Right folks, the question we have here today is based off a pyramid horn antenna, it's saying, and what we have to do is we have to complete a one-piece surface development of the actual structure. Okay, so I'll start off by just reading the question and then breaking it down. So it says a pyramid horn antenna as shown in the graphic, so we can see it here, the graphic, and we can see the real live image of it here. Is shaped to direct radio waves in a beam. Shapes similar to this are widely used in such devices as radar guns and automatic door openers. Now it says the antenna contains a sheet metal transition piece between two rectangular openings. So we can see here that the base is rectangular and the top part of it is rectangular. But if you actually look at the elevation and the plan, what they've left out is, you can see this little bit here at the top, they've left that out obviously of it. So they're just talking about this little bit of it here. And it says the antenna contains sheet metal transition piece between two rectangular openings. The projections of the transition piece are given. So you can see the elevation and plan view here. Complete a one-piece surface development of the transition piece. Okay, so similar enough to other questions that we have previously done, only that in this case it might seem a little bit easier in the fact that we've actually only got four, whereas four kind of pieces to it to actually develop out. Whereas in other questions we might have had 6 to 8 to 10. Now, if you look at it, we have side 1 here, 2, 3, 4. We obviously know that it's open at the bottom and it's open at the top. It's just 4 pieces, 4 sides essentially that are going to make it out. So straight away we're actually going to start off by labelling the problem. So part 1, 2, corner 3, 4, and if I did 1, 2, 3, 4 like this, I'm going to do the same with the top of it, 5, 6, 7, 8. So if I label it in elevation, I'll also label in plan. So I got 1 and 2 here, 3 is at the front, 4 is at the back, and then 7 and 8, and then we have 5 and 6. So that's the problem labels there. Now, if we take that structure and we're going to basically develop it out, what we need is true lengths as usual. Straight away looking at this, I can see that the bottom of it is a rectangle. It's all sitting on the ground. They're all parallel with the XY line, so 1 to 4, that's a true length. 1 to 2 is a true length. These are all true lengths the whole way around, as it is on top. So 1 to 2, 2 to 3, 3 to 4, 4 to 1, we can take them as true lengths. 5 to 6, 6 to 7, 7 to 8, 8 back to 5 is all true lengths. Now the only other lines that we actually have in this problem is 5 to 1, 6 to 2, 7 to 3, and 8 to 4. And just by looking at that, I can see that every one of them is the exact same length as well. So if I find, and none of them, but the only thing is actually, I should say, in plan, none of them are true lengths. In my elevation, they're not true lengths either. And the reason for that is because in plan, the line, let's take it just the line 1 to 5, that is not parallel with my XY line. And if it's not parallel with my XY line, well then that 1 to 5 in elevation cannot be a true length. And it's the exact same when we work it the other way. 1 to 5 in elevation is not parallel with my XY line, so therefore in plan it can't be a true length either. So what I need to do is I need to find the true length of the line 1 to 5. And if I find that true length of the line 1 to 5, then that's going to work out the same length for 6 to 2, 7 to 3, and 8 to 4. So we'll start off by doing that. Now, I'm going to take, in this case, the way I'm going to work it is 5 is the apex of a cone. So to actually work out that, if I'm going to do that, or actually what I'll do, I'll flip the cone upside down. So if we imagine we had this time not a right cone but an inverted cone, I'm going to take 1, which is on the ground, as the apex of a cone, and in this case a cone that is upside down is going to be a triangle that's kind of going something like that. So if 1 is the apex of a cone, I want to get the true length of the line 1 to 5. So I need to make it a generator. So going to bring 1 out, when the relationship between that line there that I've just drawn and this line here, which is the XY line, is that it is parallel. And from 5, because anytime I look down the cone I see a circle in plan, so from 5 I'm going to rotate around, making a mock part of my cone. So where 5 is rotated to is now here. That is the new position of 5. That would be the extreme generator of our cone. And what I need to actually do is I'm going to bring 5 up. And the new position, because remember 5 was up here, the new position of my 5 is actually out here. That is the new position of my 5. And if I join that back to 1, that will give me a true length of the line 1 to 5. That there is my true length of the line 1 to 5, which is the same as 6 to 2, 7 to 3, 8 to 4, or however you want to call it, 4 to 8. So that is just a cone obviously working in the other direction. Obviously this is an inverted cone, so in this case my cone would be, the apex would be here, the generator, that is the extreme generator, out here. Okay, I'll actually just put that in definitive color so we can kind of see it a bit better. That's my true length from there to there. Okay, now at this point I'm going to start completing the surface of element, because at this point we have the true lengths of all of these lines. I have the true lengths of 1 to 2 and so way around, 5 to 6 around, and I've got the true length of 1 to 5, which is the same. So I'm going to pick a start point and I'm going to say right about here. I'm going to pick that as point number 1, the easiest one. So straight away I can take the distance from 1 to 2, which is that distance there, and I'm going to step it down here somewhere. So somewhere down along there is 2, and at my 1 I'm going to drop a line straight down, and there is my 2 right there. Now, do I have the true length from 1 to 5? Yes, I do. I found that up here, my elevation. So I'm going to find that, and from 1 somewhere out there is my 5. Now the question is, at this point, where exactly is it? Is it here? Is it here? Is it here? Is it here? Okay, don't know at the moment. Do I have the true length from 2 to 6? Yes, I do. Now, same thing. 6 is somewhere along that arc. Do I know exactly where it is at this moment in time? And the answer to that is no, because it could be here, it could be here. And the thing is, we do have 5 to 6 as a true length, which is from there to there. But it's hard to determine. If I started that, then my 6 would go up like this, and we're not exactly maybe getting the true shape of that structure, of that actual side of it there. So what I can use here is the triangulation method, which is very similar to what we have previously done on other questions. Okay, so what it means is I'm just going to have to get one more true length. So I'm just going to put this in here. Okay, and I'm going to create a triangle inside in this surface here. I'm actually going to split it up and make it into 2 triangles. Now, all I have done there is I have joined 5 to 2. And if you actually look, I've created a triangle, 1, 5, 2. But now what I have done is I've created a straight line going across the face of 1, 5, 2. So if we actually just look up here and we were to label it as well. Remember 1 and 2 were on the ground, so that would be my 1, that would be my 2, my 5 would be here, and my 6 would be here. And as I said, we had the true length of 1 to 2, we have the true length of 5 to 6, and we have the true length of these lines. However, we weren't able to determine exactly when we did the arc the exact point positioning of 5 or the exact positioning of 6. So what I have done now is I've essentially drawn a line across the face there, like that. I have drawn a line, and as you can see I've split it up into 2 triangles, 1, 2, 5 and 2, 6, 5. But what I want to now get is the true length of the line from 5 to 2, and we can actually do that very simply by literally using the same method that we have previously done, which is with cones. Okay, so in this case I'm going to take the line from 5 to 2 as the apex of a cone. Okay, but watch, I've already got 5 out here. Another way we could actually get the true length, and this is very useful for us, if we have 5 as the apex of a cone, and let's say, just discard this, now we have that true length got for 1 to 5, which was working for the rest of them, but if I take 5 as the apex of a cone, I'm going to have a triangle going out something like that. And when we draw it in plan, if 5 was the apex of a cone, my radius would be from 2 around like that. So what I can do is, where 5 is, and you can see my straight line down here, another way of getting the actual true length of it is I could take the distance from 2 to 5 there, I could take that distance on my compass, and where it hits the XY line over here, I'm going to step it out. And what I'm going to do is I'm going to join that now back to 5. and once again just put it in a little bit heavier. Two arrows, and that now is my true length, and I'll write it this way, of my line from 5 to 2. There we go. Very important. Now, I have 1, I have 2, I have the true length from 5 to 2, and we knew 5 was somewhere along this arc previously, as I said. So, I can take the distance, the true length from 2 to 5, or 5 to 2, however you want to call it. I can take that distance now on my compass, and at positioning of 2, there we go. I can now call that point there 5. Okay? I can now join that to 1. And if I wanted to find 6, I could take the distance from 5 to 6, right there like that, and at 5, that's exactly where my 6 will be, right there. Okay, and there we go. That is the first face of the structure complete. And once again, if you want, I can put in the line from 5 to 2 and it will break it up into those triangles. I'll just put this in a little bit lighter, but you can kind of see it there. Okay, that is the true shape of that face there, but it is the development of it. Okay, now we have done this one here, so now we're getting on to 2, 6, 7, 3. So same thing again, use the same sequence now. So I'll get the line 7 to 3, or sorry, 2 to 3, apologies, and somewhere out along there, somewhere out along that arc, sorry, down now so you can see it, somewhere down here along that arc is my 3. Do we know exactly where it is? Once again, no, we don't. We do though have the 6. Okay, so we do have the line 2 to 6, and I do also have the true length from 6 to 7. So I'll just put that in while I'm at it. So somewhere along that arc there is going to be my 7. Obviously, as I said, somewhere along this arc from my 2 is going to be my 3. Now, at this point, we can see we're obviously running into a little bit of a problem here because we don't know exactly where along these arcs that our points are going to be. So what I could do is, once again, I could join a line here. This is called a triangulation method because what I'm actually doing is creating triangles on the surface. I could join a line from 6 to 3. Very simple. And what I could do then is I could get the true length of that line, and from 6 then with the true length I could find my 3 down here. So with that 6, if I take 6 as the apex of a cone, once again, so I've got my 6 up here. See it there? And like the last time I did, I took this distance, if you remember here, I took that distance and I stepped it out over here. Like the last time, I'm going to use that method again. We could rotate up as well. You could rotate up. But what I'm going to do is I'm going to take this distance, and I'm going to show you the two methods in one. I'm going to take the distance from 6 to 3 on my compass, where it is on the XY line here, right there, I'm going to step it out. And it hits right there. Now, I'm going to join that to 6. Same thing, I'm going to just put it in a little bit heavier. And that is my true length from 6 to 3. Okay? Now, that is the method of literally just taking 6 as the apex of the cone. I know my radius and plan for basically being able to draw my cone. I just took that, came up here, and I stepped it out. Another method you could do there, and it will give you the exact same result here. Once again, we know if we did the extreme generator method of a cone, and use 6, as I said, as the apex of a cone, we look down at it, we see a circle. If I got 3 and rotated it up, 3 would literally come to there. This is the exact same method, and I would bring that up. But it gives us the exact same result. That's just the two methods, and it's just showing you another way of getting it. I don't always have to rotate it up. It's literally a case of I took the radius, and I came up here and I stepped it out. Okay? So that's the two methods. Now, I have that true length got. It was very important. this true length running across the face from 6 to 3, and I'm going to take that true length now on my compass, which is there, and at 6 I'm going to bring it across until it cuts through my 3 arc, and right there now is my 3. 3 we know joins the 2. Okay, have I got the true length from 6 to 7? Yes, I do. Have I got the true length from 3 to 7? Yes, I do. Because if you remember, my 3 to 7 was the same true length as my 1 to 5. So I can just come back here and get that 1 to 5 one. And go on to my 3. And there we go. And that there now is my 7. We'll join it up. And that now is 2 faces of my problem complete. And if you wanted again 6 to 3, I could put it in. I'll just put it in lightly for now. And you can see how we're using, look, it's a triangle, a triangle, a triangle, a triangle. But we obviously only want the square structures. Now at this point, just to make it a little bit more clear, I'm going to start having in some parts of it. Okay, now you might ask, why didn't I heavy in or hatch in these lines here in the middle? The reason I didn't is because those lines aren't actually fold lines on the object. I just use those lines basically, it's the triangulation method, and I only put them in there for your understanding. They are not actually needed on this development. They are only needed to help us actually locate the final points of, remember when we were finding 5 to 2 and 6 to 3. Now, at this point here, it's the exact same thing now. I'm going to try and complete the rest of the question, just using that triangulation method problem or solution. Okay, so we're at 3, we'll try and find 3 to 4. So, somewhere from 3 out here is going to be my 4, somewhere out along that arc. Now, same thing, at 7, which I have up here, is my 8. And somewhere out along that arc is going to be my 8. The problem is we don't know exactly where along this arc is 4. We don't know exactly along where this arc is 8. We do have the true length from 4 to 8 because that was the same as 1 to 5. However, we can't use that yet because we don't have any position on any exact point on 1 or 2 of these arcs. So once again, we can do a triangulation method. Now, instead of just making up another one and having to find another exact one, if I think back to junior cycle graphics, I can use axial symmetry. So, if we look at 2 and 5 here, now this structure here, this face, is the exact same as this, only it has literally been flipped. So, if we take that as well, 2 to 5, if I flipped that 5 in this case would be where 8 is, and 2 will be where 3 is. So, if I join 8 to 3, that essentially means instead of having to work out the true length of 8 to 3, we actually, if we're just smart and think about it, we already have it. And because that is the same as the true length from 5 to 2, which we already found to be over here when we worked it out earlier. So it's just using a little bit of smarts to be able to figure it out. So I'll take the true length from 5 to 2, which we have now just realized is the same as the one from 3 to 8. So if I go from 3, because I already have point 3, remember, so from 3, there we go. I have now just found where it cuts through the arc 8, and straight away there I'm going to just heavy that in. Now I have the true length from 8 to 4, which was my first true length that I found, which is the same as the one from 1 to 5. There to there. Take that onto 8, and there's my 4. And once again, we'll heavy that in. And what's connecting them then is another fold line. Try and keep this neat and tidy. And if you had wanted, once again, 3 to 8, that was just to put it in, just for understanding purposes, was my other triangulation line. So once again, you can see we have triangle, 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 triangle. Okay? But I'm not having it in. Now, same thing, complete the last part of the question. From 4 to 1, take true length. Somewhere along there is going to be my 1. And also from 8 to 5. Somewhere along there, that arc is going to be my 5. Now, same thing again. We don't know exactly where the 1 is. We don't know exactly where the 5 is. So what we need is a point, a line joining them. So, once again, if we think of axial symmetry, think of this surface here. Okay, that surface there is the exact same as that surface there. It's just a case of, once again, flipped over. So if we flip it over, the same thing, you can see the triangulation line that we put in here. The 3 becomes the 4, the 6 becomes the 5. Therefore, the line 4 to 5 is the same true length as my line 3 to 6. Do we have the true length from 3 to 6 already? Yes, we do. So the true length from 3 to 6 we found was this guy over here. So I'm going to get him on my compass. And now it's the true length from, that's the same as the true length from 4 to 5. Do I have 4 already? Yes. And that is cutting where the 5 is, which is along this arc here. So I'll go from 4. And where the 2 arcs cross each other, I have now found 5. So once again, I can heavy that in. There we go. Heavy it in a little bit further. Okay. Now I need to find 4 back to 1. And I have the true length from 5 to 1. That was the very first true length that I found, which is there. So now that I had 5, or I found 5, I can now find 1. And we can see right there is 1. So just to finish the problem now, heavy it in. And there we go. That is the question completed. And once again, just for understanding purposes, 5 to 4 would have been my triangle split up. And there we go. So we can see we have 8 triangles up here in our plan. 1, 2, 3, 4, 5, 6, 7, 8. And I also have 8 down in my surface development. 1, 2, 3, 4, 5, 6, 7, 8. So, important question in the sense that what we have used there is a new thing called triangulation methods, whereby we have split up 4-piece structures, surfaces, and we have divided them up into 2 triangles, essentially. Okay, and we have used the cross line between them to get to determine the true length of that, to be able to determine points that we needed. Okay, very important there. And it's just also as well, the other thing that we learned was the 2 methods as well for determining the true lengths. One was the cone's principle, the other one was the cone's principle but without the rotating of it. Okay, very important question. I hope you found it helpful. Question complete.